My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 606. In this lecture, I will continue my discussion on convolution layer in neural networks. Before understanding this lecture, I request you to go through my previous lecture, that is 605. Convolutional layer looks like this. I have an input image which is n cross c size. On top of it, I can have multiple kernels. Let's assume I am also doing padding. Also, let's assume stride equal to 1. S means what here? Stride S equal to 1. Let's assume all my kernels of the same size. Let it be k cross k. But I have multiple kernels. Here I have multiple kernels, isn't it? K of size k cross k. Let's assume I have padding them enough such that the output is also of size n cross n. Let's assume each of my image size is n cross n. Imagine I have 10 kernels. Let me assume I have 10 kernels here. If I have 10 kernels here, what happens? I will get 10 images. Just see. Let me assume I have 10 kernels. For each kernel, I will get an image. For kernel 1, for kernel 2, isn't it? I will get 10 images here. Image 1, image 2, image 3, so on, so forth. So I get image 1, image 2, image 3. All of them are size n cross n because I padded sufficiently. So this is how a convolutional layer looks like. The way it exactly works like this, isn't it? So convolutional layer has an input of size. What is this convolutional layer has an input of size, let's say n cross c. Let it be input size is n cross c. The output will be n cross the number of kernels. Let's assume the number of kernels is m. Let's assume the number of kernels is m. So I get, what will I get? I will get n cross m. What is this n cross n? This n cross n because I padded sufficiently and because my stride is equal to 1, isn't it? If padding changes, just let me say, if padding changes or stride changes, the size also changes. This n cross n size also changes, isn't it? And m is nothing but, what is my m here? What is my m? M is number of kernels. That's important. M is nothing but number of kernels. If I have 100 kernels, let me assume I have 100 kernels. This will become, what is this will become? N cross m means what? N cross 100. If I have 3 kernels, then this n cross m will become n cross 3. So what is this? The output, what is the output here? You will get 3D. N cross 3 means what? It's a 3D tensor, isn't it? So this output is basically again, what output you are getting? It's basically again a 3D tensor, but it's not 3 channels. Each channel in my tensor corresponding to one kernel here. So this is how a simple convolutional layer looks like. First point is, what is my first point? A convolutional layer has multiple kernels, all of the same size, isn't it? In some cases, the sizes can differ, but for simplicity, let's assume that sizes are all of same. That's the first thing. Second thing is, I need to take care of padding and strides, isn't it? I must take care of padding and strides. And what I get here is my input here is a, what is my input here? My input here is a 3D tensor if this is an RGB image, it's a 3D tensor with 3 channels, and my kernels are, what is my kernels? My kernel is K cross C, isn't it? My kernel is K cross C. My kernels are also K cross C, because this should match. Which one? Your N cross C. These two should match. Which one? Just observe. This and this should match. That we already discussed many times, isn't it? If I have M kernels, let me assume if I have M kernels, let it be M, let me assume I have M kernels. What I get basically a 3D tensor which is of size N cross M. Remember the length. Just try to understand the length. Just see. Remember the length and width. What is the length and width of this output? The length and width depend on padding. Length and width depends on padding, stride and kernel size, isn't it? Your depth, what is this? Your depth here, which is equivalent to M. M depends on the, your depth depends on the number of kernels that you have, isn't it? The question here, it could be how question here, it could be how many should we take. That's the hyperparameter, isn't it? That we will learn how to figure out using hyperparameter optimization, isn't it? So in one convolution layer you have lot of hyperparameters. Number of kernels is, what is this? Number of kernels is a hyperparameter, isn't it? What padding to apply is hyperparameter. Just see what are the hyperparameters? Number of kernels is hyperparameter. Second one is what padding to apply is hyperparameter. What should be your stride is hyperparameter, isn't it? What should be your stride is also hyperparameter. These three are hyperparameters. Now, as operation concern, the first step is how is the output generated. The output is not just a simple convolution. There are two stages to it. Okay, the first stage is take the input. Just see, the first stage is take the input. And convolve with the kernel. Let's say kernel 1. Just see, kernel 1. Second, let's assume in step 1 your input is N cross C and kernel 1, and your kernel 1 is K cross 3 with all sufficient padding and stride equal to 1. So what do you get here? You get an image which is of size N cross 1, isn't it? Which is of size N cross sufficiently padding, so that you are sufficiently padding so that your input and output is of same size, that N cross N, because it is just one image. So you basically get a matrix. This is just one kernel, isn't it? This is kernel 1. In step 2, what I do is I take this matrix, I take this matrix. Yes, in step 2 what I do is I take this matrix N cross 1 and I will perform element wise. What will I do? I will perform element wise activation like ReLU. So I take this, actually what will I do? I will perform element wise activation ReLU and I will put values here, isn't it? I will take on this one, I will apply element wise activation ReLU and I will keep here, isn't it? Applying ReLU on top of this particular, applying ReLU on top of this matrix, and I will keep values here, isn't it? Anyway, we will try to understand by element wise. I will get final matrix, isn't it? Just see what do we do in multi-layer perceptron? Just let me compare your CNN convolutional neural network with MLP multi-layer perceptron. First step is we will calculate W transpose X. Just try to recall what is my first step in this one. W transpose X, Z equal to W transpose X, where which is that dot product. W transpose X is basically W dot X. It's a dot product. Second, we'll take ReLU. isn't it? Even here, for every kernel, you take the input matrix and apply. For every kernel, you are taking input matrix and you are applying convolution, isn't it? You are applying convolution, which is like dot product. Applying convolution is just similar to dot product, isn't it? Just like W transpose X in multi-layer perceptrons, isn't it? This matrix and this matrix, this matrix and this matrix is same, isn't it? In step 1, I have got output n cross 1 that I am taking in step 2. Same matrix on which we are applying element wise ReLU, isn't it? On individual elements of this matrix, which matrix? On individual elements of this matrix, now I will apply an activation unit like ReLU to get, what will you get? To get final results, to get final matrix, or I can say final results. So an actual convolution layer looks like this. What is this actual convolutional layer? You have your input image n cross c. First you apply convolution, isn't it? Apply sufficient padding and stride equal to 1. Let's assume I have m k cross c kernels. So this generates a cube now. This generates a 3D tensor, isn't it? What will it generate? It will generate a 3D tensor of size n cross m. You are just performing convolution. But after convolution, you perform element wise. Activation like ReLU. ReLU is most element wise activation like ReLU. ReLU is most popular. Then you will get final. Matrix, isn't it? You will get final matrix here, which is final tensor. I can say final matrix or final tensor here, which is of size n cross m. The size does not change, isn't it? The size does not change. You are taking each element here and applying. Actually, why size is not changing here? Just observe this one. Here you are taking each element and applying. You are applying element wise activation like ReLU, and you are keeping here. Therefore, size will not change. The size, this size and this size, before performing element wise activation like ReLU, before applying and after applying, you will get same size, isn't it? You are taking each element here. You are taking each element here and applying ReLU. You are taking each element and applying ReLU on top of it, isn't it? It just if you try to recall, just like in MLP, just see, the size does not change. It is just like an MLP. Just let me recall our MLP. In MLP, what happens? Just see, it's what happening here. This is equivalent to dot product in multi-layer perceptron. This stage means you are taking input image Z equal to W transpose X. Your convolution is just like your dot product. There are two steps, just like MLP. The first one is, this is equivalent to the dot product stage. The dot product is nothing but Z equal to W transpose X. This is nothing but applying ReLU on top of it. So that's the relationship. Just see here what's happening. First step, Z equal to W transpose X. Second step, applying ReLU activation function, isn't it? That's what here also we are doing. Just you are applying, just what you are doing here. Instead of dot product, you are applying convolution here. Then you are performing element wise activation, isn't it? I request you to compare this particular diagram. This is related to multi-layer perceptron, where Z equal to W transpose X, which is equal to W dot X. Here you are saying applying convolution in the case of CNN. Second step is applying ReLU on top of Z. Here you are applying ReLU on top of this 3D tensor, isn't it? You are applying ReLU here. Just see, this is just like, this is step number 1 in MLP, isn't it? This is like step number 2. What is step number 1 and step number 2? This is step number 1. This is step number 1. This is step number 2. Isn't it? So this is the relationship. This is the relationship between multi-layer perceptron and convex. I request all of you to go through this lecture once or twice. Why? Because this lecture explains the relationship between multi-layer perceptrons and con nets, which is very important. If you have any difficulty, please keep a comment. I will continue my discussion on convolutional layer in neural networks in my next lecture also, that is in lecture number 607. Thank you very much.